August 15, 1977, was an ordinary summer night. In a cornfield in Ohio, USA, a radio telescope named Big Ear was operating as usual. It slowly scanned the sky, listening to radio noise from the cosmos. This massive device, constructed from a metal grid, resembled Earth's ear. Day after day, it recorded data, searching for possible patterns. At approximately 10:16 p.m., the telescope's receiver was pointed toward the constellation Sagittarius. A signal suddenly appeared. It was not the random cosmic background hiss. Instead, it was a powerful, pure, and concentrated burst of radio waves. This signal lasted a full 72 seconds. Its intensity traced a steep peak on the recording paper. The signal's center frequency was 1,420 megahertz. This frequency corresponds to the emission line of neutral hydrogen, the most abundant element in the universe. Any astronomical civilization possessing basic radio knowledge would grasp the cosmological significance of this frequency. It resembles a universal channel for cosmic communication. Days later, astronomer Jerry Emin, reviewing the data printouts, was stunned by this exceptionally prominent signal sequence. He circled the signal group in red ink along the margin of the printout and scribbled beside it, "Wow." This casual annotation became the code name for one of astronomy's most famous enigmas. The WOW signal exhibited all the hallmarks of an ideal artificial signal. It was narrowband, meaning it occupied an extremely narrow slice of the radio spectrum. It was coherent, indicating a highly consistent source. Its intensity exceeded background noise by more than 30 times. Yet the most perplexing aspect was that this signal appeared only once. Over the following decades, astronomers worldwide repeatedly pointed telescopes at the same patch of sky, yet never again detected any echo of it. It was like a shout in the cosmos, uttered once and then plunged into eternal silence. This fleeting signal became an unresolved question. Was it a natural astrophysical phenomenon from a distant galaxy? Or was it the first accidental glimpse of a voice from another civilization? For nearly half a century, the identity of the WOW signal remained an open mystery. It lay quietly in the archives, awaiting the key that could unlock its secrets. Fast forward to 2025, the astronomical community buzzed with excitement over a new discovery. An interstellar visitor was entering our solar system. It was named 3I Atlas. This designation follows the naming convention for interstellar objects. The 3 signifies it is the third such object confirmed by humanity. The I denotes its eternal interstellar origin. Atlas's orbit is an extremely open hyperbola. This means it is not bound by the sun's gravitational pull. Originating from distant interstellar space, after traversing our solar system, it will embark once more upon an endless interstellar journey, never to return. Preliminary observations indicate Atlas is a massive object, possibly exceeding 5 kilometers in size, far larger than the 2 interstellar visitors discovered previously. Its discovery immediately became the focal point of global astronomical observations, as scientists began calculating its precise orbit and tracing its origin. An incredible coincidence gradually emerged. Atlas's flight path pointed toward Sagittarius. More specifically, it originated from a coordinate in the sky we know all too well. That very coordinate matched the direction from which the WOOF signal had arrived 48 years prior. Orbital dynamics calculations can trace a celestial body's past positions with extraordinary precision. The results revealed that in August 1977, when the Large Aperture Telescope captured that famous signal, 3I Atlas was precisely located in the outer solar system, approximately 600 astronomical units from Earth. This distance lies far beyond Neptune's orbit, yet it falls precisely within the plausible range for transmitting a signal to Earth that could be detected. The dual coincidence of direction and timing has brought what was once considered science fiction into the realm of serious scientific inquiry. Did we receive a messenger's call 48 years ago? And is that very messenger now arriving at our doorstep? This possibility challenges our understanding of cosmic solitude. It is no longer a philosophical speculation but a scientific hypothesis verifiable through observation. The following narrative will center on this core question. We will examine all evidence, from orbital mechanics to spectral analysis, from dust distribution to mass estimation. We will encounter a series of anomalies that defy perfect explanation by existing astronomical knowledge. Each anomaly is like a puzzle piece. Together, they point toward a revolutionary conclusion that may redefine humanity's place in the cosmos. Whatever the final answer may be, we stand at a historic threshold. On one side lies the familiar, solitary solar system of the past, and on the other, a new universe potentially teeming with dialogue and visitors. The clock is ticking. 3i Atlas is hurtling inward at 60 kilometers per second. Our telescopes are locked onto it. Human civilization may be facing its first final exam, and we are all witnesses to this test. When two independent deep space enigmas converge across space-time, even the most rigorous scientific minds tremble. This is no longer isolated curiosity, it heralds a potential paradigm shift. In this chapter, we become cosmic detectives, placing the 1977 WOW signal and the 2025 interstellar visitor 3i Atlas under scientific scrutiny. We examine whether the chain of evidence linking them is to grasp why the WOW signal remains so hauntingly compelling. We must first understand what makes it truly extraordinary. It is far from ordinary cosmic static. Its series of characteristics point precisely toward a possible artificial origin. First is its astonishing intensity. In radio astronomy, signal strength is measured in Jansky units. The WOW signal reached a peak intensity of 30 Jansky, over 30 times the background noise. This is akin to someone clearly shouting your name in a noisy cocktail party. Such a sudden surge in intensity is extremely rare in natural astrophysical phenomena. Second, its precise frequency and bandwidth. The signal is almost entirely concentrated at 1420 MHz, with a bandwidth not exceeding 10 kHz. This narrowband characteristic is a classic fingerprint of artificial signals. Natural cosmic radio emissions, such as pulsars or interstellar gas clouds, typically span broad frequencies, covering millions or even hundreds of millions of hertz. They resemble a broad brushstroke rather than a sharp needle. More crucially, this frequency corresponds to the natural emission or absorption frequency of neutral hydrogen atoms at rest. Any civilization with basic radio astronomy knowledge would recognize this frequency as the most universal identifier in the cosmos, like a watering hole where all cosmic life might pause to drink. Thus, the 1420 MHz band is internationally known as the water hump frequency and remains the most frequently monitored band in the search for extraterrestrial intelligence, SETI program. Third is its duration and profile. The signal lasted 72 seconds, exactly the precise observation window possible when Ohio State University's Giant Ear radio telescope, due to its fixed design, scans a fixed celestial region. The signal strength exhibited a perfect bell curve, first amplifying then attenuating. This perfectly matches the response pattern of the telescope's beam model sweeping across the sky over a fixed-point source. This implies the signal source itself is fixed in the sky like a distant lighthouse. As the telescope's beam swept over it, it lit up. When the beam moved away, it faded. This ruled out any rapidly moving local source within the solar system. All these features collectively point to an extremely intriguing possibility. We may have intercepted a directional broadcast from interstellar space. However, nearly 50 years of follow-up observations have yielded no repeats. This keeps natural explanations, such as an unrecognized special comet outburst or a brief, intense interplanetary flare, alive, though their likelihood is diminishing. The WOW signal remains unresolved, an anomaly awaiting explanation. Now let us turn our attention to the current visitor, 3i Atlas. To determine whether it relates to the WOW signal, we must first understand where it came from and where it is headed. This requires precise orbital mechanics. 3I Atlas's orbit is classified as hyperbolic. This fundamentally differs from the elliptical orbits of planets or comets orbiting the Sun that we are familiar with. An object's orbital shape is determined by its orbital eccentricity. An eccentricity of 0 indicates a perfect circle. Values between 0 and 1 represent an ellipse. 1 equals a parabola, and values greater than 1 form a hyperbola. The vast majority of objects within the solar system have orbital eccentricities less than 1. They are firmly bound by the Sun's gravitational pull, while Atlas's orbital eccentricity is significantly greater than 1. This implies its velocity exceeds the escape velocity at that location within the solar system. It is not a permanent member of the solar system but merely a transient visitor. Through thousands of observations gathered from dozens of observatories worldwide, astronomers can calculate its orbital elements with extreme precision. Semi-major axis, eccentricity, orbital inclination, ascending node longitude, argument of perihelion, and time of perihelion passage. This set of numbers serves as a cosmic ID card, fully defining its motion. Using Newton's law of universal gravitation and orbital perturbation theory, scientists can replay its trajectory forward or backward like rewinding a tape, projecting its path decades or even centuries into the future. The reliability of these calculations has been repeatedly validated by the orbits of comets and asteroids, their accuracy sufficient for us to confidently assert its precise location at some point in the past. The reliability of these calculations has been validated countless times through the orbits of comets and asteroids, with precision sufficient to confidently determine its exact position at any past moment. When scientists traced 3I Atlas's orbit back to August 1977, a breathtaking coincidence emerged. Calculations revealed that on that historic night, as the Great Ear Telescope's beam swept across the Sagittarius constellation, 3I Atlas was cruising in the deep reaches of space. Approximately 600 astronomical units from Earth, almost directly facing our planet. 600 astronomical units is an unimaginably vast distance. It is 600 times farther than Earth's distance from the Sun, extending beyond the Kuiper Belt and even touching the theoretical inner edge of the Oort cloud. Yet this distance is not beyond reach for radio communication. The alignment of direction and time is tantalizing, but science demands quantification of such coincidence. Professor Avi Loeb, an astrophysicist at Harvard University, and his team conducted a rigorous probabilistic analysis. They first pinpointed the source location of the WOW signal in the sky, a precise point defined by right ascension and declination. Next, they calculated the projected position of 3I Atlas in the sky in 1977. The angular separation between the 2 points on the two-dimensional celestial sphere was merely a few degrees. Considering the total sky area of 41,253 square degrees, the probability of 2 random points aligning within such close proximity was calculated to be less than 1%. Specifically, approximately 0.6%. This implies a probability exceeding 99% that this correlation is not random. Yet this represents only geometric alignment. Another crucial piece of evidence comes from the signal itself. Returning to the question of gigawatt-level power, what transmission power would be required to send a signal detectable by the Giant Ear Telescope at a 30 decibel intensity from a distance of 600 astronomical units? Calculations indicate this necessitates a source with peak power between 0.5 and 2 gigawatts. This equates to the output of a large nuclear power plant or the world's largest hydroelectric dam. Known astrophysical processes capable of generating such intense radio radiation, such as quasars, active galactic nuclei, or gamma-ray burst afterglows, are accompanied by violent, broadband electromagnetic emissions lasting hours to days. Yet the WOW signal was brief, narrowband, and isolated. Crucially, these natural phenomena typically manifest optical or other spectral signatures. Whereas the WOW source region remained, could an interstellar object transiting the outer solar system be such a powerful narrowband signal source? From an energy perspective, It is engineering-wise conceivable that 3I Atlas could carry some nuclear-based or other advanced energy-based transmission device achieving gigawatt-level power output. This is far more plausible than hypothesizing an unknown cosmic natural phenomenon lasting 72 seconds before vanishing forever. Furthermore, the signal exhibited a slight blue shift, indicating the source was moving toward Earth at approximately 10 kilometers per second. This direction and magnitude align with Atlas 3I's relative velocity relative to Earth at the time. Though not perfectly consistent, it provides another supporting piece of circumstantial evidence. When we juxtapose these clues, the extremely improbable spatial alignment, the signal characteristics highly consistent with an artificial source, the immense power required, and the compatibility with an interstellar object's identity, a once seemingly outlandish hypothesis gradually gains scientific substance. Could 3I Atlas be the messenger that briefly greeted us 48 years ago? Perhaps it was conducting routine status reports or scanning the inner solar system when Earth happened to enter its field of detection. Thus, that cosmic hello spanning 100 astronomical units was fortuitously captured by us. It then fell into prolonged radio silence, continuing its course until rediscovered by us today. Though astonishing, this concept is not mere fantasy. It rests upon verifiable, calculable physics and orbital mechanics, offering a concrete potential source for the wow signal that subsequent observations could test. Yet this is only the beginning. If 3I Atlas is indeed that messenger, we face not merely an interstellar rock or ice body, but a complex object bearing unknown technology and purpose. In the following chapters, we will examine this visitor, examining whether its actual behavior supports this more radical identity hypothesis. While orbital mechanics outlines the macro-level connections, spectroscopy, this sharp dissecting tool, will reveal the most microscopic secrets of matter. It allows us to traverse billions of kilometers of void and directly decipher an object's chemical identity card. In this chapter, we delve into the spectral data of 3I Atlas. There, we discover not the familiar, simple combination of cosmic dust and ice, but a series of chemical anomalies that challenge our understanding. These anomalies seem to point to some unnatural, pointing to a possibility that excites and unsettles us in equal measure. Cosmic barcodes, the language of light and matter. Before delving into Atlas's specific composition, we must understand how scientists determine the structure of distant celestial bodies. The answer lies within light, more precisely within its spectrum. When light emanates from a star or reflects off a celestial object, passing through gases emitted by comets, the atoms and molecules within interact uniquely with the light. They absorb or emit specific wavelengths, leaving behind distinctive spectral lines akin to fingerprints. Imagine passing a beam of white light through a prism. It unfolds into a rainbow-like continuous spectrum. If this light passes through sodium vapor before reaching us, two adjacent dark lines appear at the specific yellow position of this rainbow. These are sodium atom absorption lines. Conversely, if the sodium atoms themselves are excited to emit light, bright emission lines appear at the same yellow position. Every element, every molecule, possesses its own unique set of spectral lines. They function like barcodes pre-programmed by the cosmos. Astronomers couple telescopes to spectrographs to collect faint light from the 3I Atlas, dispersing it into a spectrum. By deciphering the patterns of these bright and dark lines, we can precisely determine the composition of an object billions of kilometers away. This forms the bedrock of modern astrochemistry and represents our most powerful tool for examining the intrinsic nature of this interstellar visitor. Chemical imbalance, the peculiar ratio of carbon dioxide to water ice. The James Webb Space Telescope, with its unparalleled infrared vision, provided the most detailed spectrum of 3I Atlas. When the data was analyzed, the first perplexing anomaly immediately emerged. The proportions of its volatile components were severely imbalanced. In typical solar system comets, water ice is the absolute dominant component, usually accounting for over 80% of all volatiles, followed by carbon dioxide and carbon monoxide. Yet Atlas III's spectral lines tell a completely different story. Carbon dioxide overwhelmingly dominates its composition at 95%, while water ice is abnormally scarce at only about 5%. This is a completely inverted ratio. Scientists immediately proposed the cosmic ray decay hypothesis. They suggest that Atlas, having traversed interstellar space for billions of years, has endured continuous bombardment by high-energy cosmic rays on its surface. These particles may have disrupted the molecular structure of water ice, converting it into more complex molecules or directly causing hydrogen atoms to escape. The remaining oxygen atoms then bonded with carbon to form carbon dioxide. While plausible, this hypothesis faces challenges. If only the surface were altered, as the comet approaches the sun and begins the active surface material is blown away, we should observe a gradual increase in water-ice proportion, revealing more primitive internal components. However, observational data shows that as Atlas approaches, carbon dioxide's dominance not only persists but intensifies. Its emission rate increases at an astonishing power law of -9 per unit distance from the sun, far exceeding the typical comet range of -2 to -3. This suggests its interior may be uniformly rich in carbon dioxide, not just its surface. Another possibility is that it formed in an exceptionally cold and unique region of the protoplanetary disk, where carbon dioxide ice is more stable than water ice. Yet such environments are not mainstream in planetary formation models. More puzzlingly, another interstellar visitor we encountered, 2I Borisov, exhibits composition strikingly similar to solar system comets. Why is 3I Atlas so singularly distinct? These questions cast a significant doubt on the first chemical anomaly. Industrial fingerprints, pure nickel and missing iron. However, the real climax of the debate came with discoveries from the UV and optical spectrograph of Chile's Very Large Telescope. Led by Thomas Pausel and colleagues, clearly detected emission lines from neutral nickel atoms in Atlas's coma, a total of 22 distinct spectral lines. All lines perfectly matched the fluorescence produced when nickel is excited by solar ultraviolet radiation. Yet the spectral lines for iron, which typically accompany nickel, were conspicuously absent. This discovery sent shockwaves through the astronomical community. In the natural cosmos, nickel and iron are almost always inseparable. Both are ultimate products of nuclear fusion within massive stars and are ejected in vast quantities into the universe during supernova explosions. In the planetary systems that subsequently form, these two elements, due to their similar chemical properties, also coexist closely in minerals. Nickel-iron alloys are common constituents in asteroids, comets, and planets themselves, detected in any solar system comet studied in detail. While their proportions fluctuate, nickel and iron have never been observed in isolation, never as nickel alone with iron entirely absent. This phenomenon points to a non-natural explanation. On Earth, pure nickel devoid of iron is a product of standard industrial refining processes. For instance, in the Mond process, carbon monoxide reacts with impure nickel at moderate temperatures to form volatile nickel carbonyl gas. At higher temperatures, this gas decomposes, depositing extremely high-purity nickel metal while leaving impurities like iron behind. This process is widely used to produce aerospace-grade high-performance alloys, electronic components, and ultra-high-purity nickel required in numerous high-tech fields. Nickel carbonyl itself is a known compound that may sublimate at lower temperatures. As comets approach the sun, their emission rates surge dramatically. Under ultraviolet radiation, this decomposition produces the observed pure nickel atomic emission lines. However, the critical question remains: how nickel carbonyl forms in the natural space environment and exists in such pure form is a major mystery. It requires specific temperature, pressure, and chemical conditions that are extremely difficult to achieve in the cold outer regions of protoplanetary disks or interstellar space. The VLT team cautiously suggests this opens a door to a new world of chemistry, but Avellard et al. State more directly that nickel without iron is a strong indicator of industrial processing. It aligns more with our expectations for technological products than natural rock. Dynamic evolution, color changes, and active outbursts. The chemical anomalies are not static. The visual appearance of Comet 3I Atlas is also undergoing dramatic changes. In early September, multiple astronomers reported its color shifting from a previous reddish hue to a vivid green. Green hues in comets typically originate from diatomic carbon molecules or cyanide groups. These molecules emit characteristic green light when excited by solar radiation in the thin coma. Spectroscopic observations confirm this. Cyanide production in Atlas's coma is surging, synchronized with increased nickel emissions. Such color shifts are not uncommon. Many comets turn green when nearing the sun, but linking the timeline with chemical composition paints a peculiar picture. Both cyanide and carbonyl nickel emissions are increasing along an unusually steep curve. It suggests either a layered structure within the object or a heat-triggered mechanism systematically releasing different substances. This bears greater resemblance to a meticulously engineered system. Perhaps its surface is coated with a layer that sublimates only at specific temperatures. As solar heat penetrates deeper, successive layers activate sequentially, exposing fresh material beneath. Alternatively, these emissions may not stem from simple ice sublimation, but from internal processes like propellant leakage or byproducts of waste expulsion. The convergence of clues points toward a technological chemical narrative. When we assemble all these chemical clues, a coherent yet unsettling picture emerges. An object exhibiting an anomalous CO2 to water ice ratio suggests it likely did not form within our familiar solar system environment. It is emitting pure nickel, a substance virtually impossible to find in nature, strongly suggesting some form of industrial-scale refining or processing. The extreme and synchronized bursts of activity in all its chemical emissions indicate an extraordinary internal structure or triggering mechanism. Individually, these chemical signatures might each be explained by some extremely rare or unimagined natural process. But when we must stack a series of improbable events to piece together a natural explanation, the overall credibility plummets. Occam's razor begins to tilt the other way. The simplest explanation may no longer be that this is a super-rare comet with multiple unusual traits, but that it isn't a comet at all. Spectral data cannot directly reveal the purpose of this object, but it provides compelling indirect evidence that it has undergone or is undergoing non-natural processes. Its material has been screened, separated, and purified, a hallmark of technological civilization. What we observe may not be a naturally formed cosmic fossil, but a manufactured artifact. Its anomalous chemical composition is precisely the manifestation of its factory label and industrial imprint. As 3I Atlas continues its plunge toward the sun, these chemical signatures are expected to intensify or evolve. Our telescopes will remain trained upon it, recording every spectral detail. The next time it reappears from behind the sun, we may obtain decisive data to confirm or refute this startling hypothesis. That we may have, for the first time, touched extraterrestrial technology through chemical analysis. When multiple anomalies point toward a disruptive possibility, we require a robust framework to distinguish rigorous scientific conjecture from wild fantasy. Assessing extraterrestrial technology hypotheses is not a simple choice between belief and disbelief, but a systematic endeavor involving scientific philosophy, risk assessment, and rigorous logical deduction. This chapter will construct such a framework, exploring how to find that subtle yet crucial boundary between extraordinary claims and extraordinary evidence. One core principle of scientific inquiry is Occam's razor, which suggests favoring the simplest hypothesis requiring the fewest assumptions among competing explanations. At first glance, interpreting the 3I Atlas as a peculiar comet exhibiting multiple rare characteristics seems simpler than attributing it to extraterrestrial technology. However, when the ad hoc assumptions needed to explain these anomalies pile up, when we must repeatedly invoke unprecedented chemical processes, extreme coincidences, and statistically improbable orbital parameters and dimensions, the simplicity of this naturalistic explanation begins to unravel. It becomes cumbersome and convoluted. At this point, another possibility that we are confronting a single cause, a technological artifact of intelligent design, begins to exhibit a certain conceptual elegance. Occam's razor does not always favor the conservative explanation. When anomalies accumulate to a certain degree, the simplest explanation may well be the one that unifies them all. Yet, the scientific spirit demands extraordinary claims be supported by extraordinary evidence. To systematically assess the strength of such evidence, Professor Avi Loeb proposes a 0 to 10 evaluation scale. This scale is not meant to assign precise probabilities but to outline a ladder of suspicion and thresholds for action. Level 0 signifies a fully natural object where all observed characteristics align with known comet or asteroid categories. For instance, the previous interstellar visitor 2I Borisov falls into this category. It looks like a comet and behaves like one. Levels 1 through 3 indicate minor deviations potentially stemming from measurement uncertainties or insufficient data, yet still within the realm of natural phenomena. Level 4 represents a critical turning point where the object exhibits multiple independent anomalies that are difficult to explain. These anomalies collectively form a pattern suggesting a possible artificial origin, though not yet conclusive. According to Loeb's assessment, 3I Atlas currently resides at this level. Orbital alignment, chemical characteristics, retrograde behavior, and mass anomalies collectively constitute a signal warranting high attention but requiring further verification. Objects at this level demand increased observational resources and heightened vigilance. Levels 5 to 6 signify the evidence begins to tip in favor of a potential new signal or behavior unexplainable by any known natural process. Examples include the detection of regular, repeating radio transmissions or the observation of distinct geometric structures. The strength of evidence begins to exceed the 50% confidence threshold. Level 7 marks the milestone of confirmation. The object is verified to exhibit maneuvers requiring advanced technology or transmits undeniably artificial signals. At this point, the debate is largely concluded. We have confirmed the existence of extraterrestrial technology. The subsequent questions shift to its nature and intent. Levels 8 through 10 involve assessing potential threats. Level 8 represents confirmation of a harmless artificial object, possibly a flyby mission for scientific exploration. Level 9 signifies the object possesses the capability to cause regional damage, while Level 10 indicates a global existential threat, such as a large technological object confirmed to be on a collision course with Earth. Within this assessment framework, we can examine the current status of the 3I Atlas more dispassionately. Classifying it as Level 4 does not declare its identity but acknowledges its anomalous nature has reached a level demanding serious consideration. This is akin to a physician observing multiple correlated rare symptoms in a patient. Though not yet diagnosed, sufficient grounds exist to escalate from routine examination to in-depth screening. Hovering above all assessments is the ultimate question of intent. The dark forest hypothesis offers a stark yet logically consistent perspective, depicting the universe as a silent forest where all civilizations remain hidden. Any civilization revealing its existence risks annihilation by others driven by fear or preemptive motives. From this viewpoint, if 3I Atlas is indeed a technological artifact, its silence and stealthy behavior align with survival logic. It could be a silent scout, assessing whether our civilization poses a threat. Its signal from 48 years ago might not have been a friendly greeting, but rather an accidental exposure. Yet other possibilities exist. It could be an ancient, long-defunct probe drifting through interstellar space, its signal merely the final gasp before system failure. It might be a platform dedicated to pure scientific research, indifferent to surrounding intelligent life. Or it could operate according to motives and ethics we cannot begin to comprehend. Maintaining openness to multiple hypotheses before obtaining definitive evidence is paramount. Science's greatest strength lies in its capacity for self-correction. Today's wildest hypothesis may prove true tomorrow or vice versa. The current debate over 3I Atlas holds value not merely in seeking answers to a specific question, but in refining our methodology for confronting the unknown. It compels astronomers, physicists, chemists, and even philosophers to collectively ponder, When humanity truly encounters a technological artifact potentially originating from another source, how should we think? How should we ask questions? And ultimately, how should we respond? We stand at a frontier of cognition. On one side lies the familiar natural universe governed by gravity and chemistry. On the other, a potentially entirely new realm brimming with intent and design. The framework provides a map to traverse this fog. It does not guarantee we will find the truth, but it ensures we do not lose our way on the quest for it. As more data pours in, the three atlases' position on the evaluation scale will inevitably shift, whether sliding toward the mundane 0 level or ascending to disruptive level 7. This exploration itself profoundly reshapes our understanding of the cosmos and our place within it. The ticking of the clock grew unprecedentedly clear in the autumn of 2025. 3I Atlas, this interstellar visitor, hurtled toward the inner solar system along a precisely calculated trajectory. The global astronomical community entered a race against time. Multiple critical observation windows would open and close in rapid succession, each potentially yielding decisive evidence. Missing any would leave a knowledge gap spanning years. This was an unprecedented global collaborative observation campaign, from spacecraft orbiting the Sun orbital spacecraft to Earth's giant telescopes, from probes hurtling toward the outer solar system to amateur astronomers' equipment. All eyes were fixed on this bright spot that could rewrite human history. Mars will serve as the initial front line in this campaign. According to orbital predictions, the Atlas 3I will pass within approximately 29 million kilometers of Mars in early October, a distance considered a close encounter by astronomical standards. Meanwhile, multiple orbiters currently circling Mars are poised to become humanity's first-line eyes for scrutinizing the interstellar visitor's details. The most crucial player is NASA's Mars Reconnaissance Orbiter, MRO, and its high-resolution imaging science experiment, HiRISE camera. Hailed as the most powerful camera ever placed in orbit around another planet, HiRISE can resolve objects as small as 1 meter on the Martian surface. When it turns toward deep space to capture images of the 3 Atlas, despite the vastly greater distance compared to its Mars imaging altitude, it is expected to achieve a resolution of approximately 30 meters per pixel. This capability promises to revolutionize our understanding of this celestial object. Prior to this, imaging of interstellar objects was limited to blurry ground-based telescope spots. Even the Hubble Space Telescope, hindered by vast distances, could not resolve its core structure. HiRISE's observational objectives are clear and critical. Primarily, it aims to precisely measure the core's dimensions and shape. Current estimates for 3I Atlas's size range from 0.5 to 5 kilometers, a far too broad margin. Should HiRISE confirm its diameter approaches or exceeds 5 kilometers, its marked divergence from the two smaller interstellar visitors would underscore its statistical rarity. The core's shape is equally crucial. An irregular potato-like form aligns with the expected characteristics of a natural celestial body. However, if the imagery reveals anomalous geometric features, such as unnatural angular edges, cylindrical forms, or even discernible planar structures, these would provide compelling evidence supporting the technological hypothesis. Second, studying its dust and gas distribution patterns. HiRISE will clearly resolve the coma's structural details, observing whether dust uniformly envelopes the nucleus or exhibits asymmetric jets. If confirmed that dust primarily accumulates on the sunward side forming a headlight effect, rather than the traditional sun-away tail, this would corroborate Hubble's preliminary observations, further solidifying its deviation from conventional cometary physics. Concurrently, the European Space Agency's Mars Express Orbiter and Trace Gas Orbiter will join the observation effort. Their spectrometers will analyze the material composition of Comet 3I/Atlas from perspectives distinct to Earth. By comparing spectral data obtained from Mars and Earth, scientists can construct a more comprehensive chemical composition model and may even detect trace substances previously obscured by Earth's atmosphere. Yet, the Martian observations mark only the prelude. The true decisive moment arrives in late October when Comet 3I/Atlas reaches its orbital perihelion, the most active and luminous phase for any comet. Solar heat will maximally excite the sublimation of its surface ices. By conventional logic, this should be the prime window for observing its peak activity. However, orbital mechanics play an anxious trick at this juncture. For nearly 3 weeks around perihelion, Comet 3I/Atlas will traverse the far side of the Sun. From Earth's perspective, it will be completely drowned out by the Sun's intense glare. All ground-based and near-Earth orbiting telescopes will be temporarily blinded. This enforced observation hiatus forms the most perilous window of uncertainty. Shielded by the Sun, a technologically advanced object like the 3 Atlas would gain a perfect opportunity to execute critical operations undetected. Astrophysicists note that orbital maneuvers near perihelion yield maximum efficiency. The Sun's powerful gravitational field acts like a gravitational slingshot, where a small thrust can produce massive orbital changes. Calculations indicate that applying a velocity change of 30 to 40 kilometers per second at perihelion would suffice to cause it, or any object separated from it, to intersect Earth's orbit by late January. Are we witnessing a cosmic stealth maneuver? The answer will emerge in early December when S3I Atlas reappears from the Sun's opposite side. Global telescope networks will immediately triangulate its position to redetermine its orbital trajectory with extreme precision. Should the new orbit deviate beyond margin of error from predictions based on pure gravitational models, it would confirm non-gravitational propulsion. That would mark a historic moment, signifying we are indeed confronting an autonomous navigating object. Another potentially transformative opportunity in this global observation comes from NASA's Juno probe, currently orbiting Jupiter but nearing the end of its mission. Juno carries cameras and spectrometers capable of interstellar observation. More significantly, through a meticulously calculated orbital maneuver, Juno could achieve an unprecedented close encounter with Atlas III as it flies near Jupiter. This proposal has sparked intense debate within the scientific community. Proponents argue the data from a close flyby would be invaluable, enabling unprecedented surface detail resolution and potentially detecting faint radio emissions or thermal anomalies. Opponents counter that the maneuver would deplete Juno's already limited fuel supply, prematurely ending its scientific exploration of Jupiter. Moreover, the encounter itself carries risks. If 3I Atlas is indeed artificial, close contact could trigger unpredictable. At the heart of this debate lies differing perceptions of risk. Whether to settle for safe, distant observation or take a calculated gamble for knowledge that could rewrite the history of civilization. The Juno team's decision will be revealed in the coming weeks. Beyond all these official observations, a civilian science project called the Galileo Project is also making intensive preparations. Led by Professor Avi, the project aims to systematically search for and monitor anomalous objects in near-Earth space. Their observatories in Massachusetts, Pennsylvania, and Nevada will focus particularly on the vicinity of 3I Atlas's trajectory after its perihelion passage, searching for any small subprobes it might release. These subprobes could be only a few meters in size. While too faint to be detected by large official telescopes, they may become visible through Galileo Project's specialized, optimized observation equipment. The timeline advances relentlessly. October's Mars flyby will deliver the first wave of high-resolution data, followed by a communication blackout from late October to mid-November, a period of anxious waiting. When it reappears in the pre-dawn sky in early December, a new wave of observations will commence immediately. Orbit determination, component analysis, activity assessment. All these data streams will converge into a clear answer. We stand at a rare moment in scientific history, one that may be marked as a watershed in future textbooks. The Global Observation Network functions like a vast nervous system, its sensors all pointed toward a single target. Every shutter click, every spectral acquisition, contributes to piecing together an unprecedented image for humanity's collective understanding. Whatever the final image reveals, whether an extraordinarily peculiar comet or a messenger from a distant world, we are poised on the threshold of discovery. On the other side of that threshold lies a universe utterly unlike anything we have known before. As data from Comet 3I/Atlas flooded major astronomical institutions worldwide, the scientific community, typically a bastion of rationality and composure, was experiencing unprecedented upheaval. The debate over the nature of this interstellar object had long transcended mere academic inquiry, evolving into a profound contest over scientific methodology, the boundaries of authority, and the limits of human understanding. At one end of the spectrum stand official research institutions like NASA and the European Space Agency. Their public statements maintain characteristic caution. Tom Stotler, NASA's Solar System Small Bodies Research Lead, stated at a recent press conference, "To date, all observational data align with an interstellar comet exhibiting unusual characteristics." He acknowledged that 3I Atlas exhibits interesting anomalies, but stressed that directly equating these anomalies with extraterrestrial technology represents a significant logical leap. This stance reflects institutional science's rigorous adherence to evidentiary standards and deep consideration of the potential societal impact of scientific discoveries. They prefer to explain the unknown within the limits of known physics rather than hastily venture into entirely new realms of understanding. At the opposite extreme lies the possibility school, represented by Avi Loeb and his supporters. Loeb has publicly countered Stotler's arguments on multiple occasions, when 5 independent improbable events coincide, insisting it's just a comet becomes the unscientific position. He accuses mainstream astronomy of harboring a systemic conservatism, a mindset that rejects evidence, potentially overturning established paradigms. The core argument of the Loeb camp is succinct and forceful. They are not asserting that 3I Atlas is an alien spacecraft, but insist this hypothesis deserves serious consideration and should guide further observations as a working hypothesis. This debate quickly spread beyond academic journals and conference rooms into broader public discourse. On academic social media and science blogs, supporters of both sides engaged in fierce arguments. Opponents criticized Loeb for undermining astronomy's credibility and degrading serious science into science fiction, while supporters countered that vested interests were obstructing the normal scientific process. Some moderate scholars attempted mediation, urging all parties to maintain open-mindedness and let evidence, not personal stances, guide the discussion. Yet amid the polarized discourse, such rational voices were often drowned out. The intensity of the controversy became particularly evident during the academic publishing process. Several papers submitted by the Loeb team encountered unusually prolonged peer review delays. One paper on the upper limit of non-gravitational acceleration in the III Atlas was held up for nearly a week on a preprint server before release, a process typically taking only hours. Another paper detailing chemical composition anomalies was outright rejected by an editor at a prominent journal, citing excessive specialization of the research scope, limiting broad reader interest. Supporters of Loeb interpret these incidents as systemic suppression of disruptive ideas by the academic establishment. Concurrently, several prominent scientists launched unusual personal attacks against Loeb himself. Planetary scientist Steve Desch publicly compared Loeb's paper to undergraduate work and gave it a failing grade. Such personal attacks, exceeding the bounds of academic criticism, exposed the scientific community's deep-seated anxiety when confronted with paradigm challenges. As historians of science have noted, this reaction is not uncommon in scientific history. When Copernicus proposed the heliocentric model and when Wegener proposed continental drift, they both encountered similar resistance from academic authorities. Underlying this debate lies a fundamental question in the philosophy of science. How should science respond to anomalous data? Conservatives adhere to Popper's falsificationism, demanding that Loeb's camp provide conclusive evidence to validate the extraterrestrial technology hypothesis. Reformists, however, invoke Kuhn's paradigm shift theory, arguing that when anomalies accumulate to a certain extent, the old paradigm itself should be re-examined. Both sides invoke scientific methodology to defend their positions, trapping the debate in a philosophical stalemate. Notably, this controversy also exposes cognitive differences across disciplines. Traditional planetary scientists tend to seek explanations within established frameworks, while astrophysicists and SETI researchers maintain a more open stance toward the possibility of extraterrestrial technology. This clash of disciplinary cultures has both enriched the discussion and deepened the divide in understanding. Amid the scientific storm, some younger scholars have adopted a more pragmatic stance. They sidestep metaphysical debates about extraterrestrial technology, instead focusing on the unique research opportunities offered by the 3I Atlas. Whatever it is, remarked a postdoctoral researcher who requested anonymity, it represents our first direct sample of material composition from an exoplanetary system. Its scientific value is undeniable. As observational data continues to accumulate, the scales of debate are shifting subtly. High-rise images transmitted by the Mars Reconnaissance Orbiter in October revealed perplexing regular geometric features within the core of 3I Atlas. While insufficient for definitive conclusions, the clarity was enough to prompt more scientists to seriously consider the possibility of non-natural origins. Some previously silent astronomers began publicly calling for increased observational resources, arguing that regardless of the truth, this object warrants the highest level of scientific attention. The core of this scientific controversy extends far beyond identifying an interstellar object. It interrogates the scientific community's mechanisms for addressing extraordinary claims, tests contemporary science's ability to break free from path dependence, and challenges humanity's courage and humility in confronting fundamental unknowns. As one philosopher of science observed, true scientific spirit lies not in stubbornly defending existing knowledge, but in maintaining honesty about ignorance. All our current debates about 3I Atlas ultimately practice this honesty. In scientific history, the triumph of new ideas often requires waiting for defenders of old paradigms to gradually exit the stage. But 3I Atlas won't wait. It's hurtling through the inner solar system at 60 kilometers per second, leaving science with rapidly dwindling time to reach consensus. Regardless of which side ultimately proves correct, this debate itself has profoundly altered how we explore the cosmos. It teaches us that, in the face of infinite space, maintaining an open mind may be more crucial than possessing certain knowledge. As the figure of the 3I Atlas grows clearer in telescopes' fields of view, a question begins spreading from the scientific community to all of humanity. Are we ready? The answer may be unsettling. As a species, we are utterly unprepared for the possibility of first contact. Existing treaties like the Outer Space Treaty primarily regulate space activities between nations, while SETI protocols for post-detection procedures only address radio signal contact. No international legal framework or contingency plan exists for the arrival of a physical entity within our solar system. This institutional void lays bare the naivety of human civilization when confronting the cosmos. The divisions within the scientific community are now spreading to the societal level. Official bodies strive to maintain a calm, professional tone, while the media inevitably amplifies every possible scenario. Across the internet, discussions about the 3I Atlas have fragmented into countless narratives, ranging from rigorous scientific analysis to pure fantasy and speculation. This very fragmentation of the information ecosystem could amplify future crises. Should events unfold rapidly, the absence of authoritative, credible information channels could trigger global panic or chaos. Faced with this situation, governments worldwide are navigating a delicate equilibrium. Publicly, they endorse scientific institutions' routine research programs. Privately, intelligence and defense agencies are quietly conducting situation assessments. This dual-track approach reflects the dilemma confronting decision-makers. Overreaction risks triggering unnecessary panic, while underreaction could place humanity in peril. In the United States, lawmakers have proposed closed-door hearings. At the United Nations, debates are underway about whether to place the matter on the Security Council agenda. On a philosophical level, the emergence of 3I Atlas is challenging some fundamental assumptions of human civilization. If it is indeed a technological artifact, several core questions immediately arise. What is our place in the cosmos? What defines intelligent life? What makes human civilization unique? For millennia, these questions were the exclusive domain of theologians and philosophers, yet now they may be approached with empirical answers. The dark forest hypothesis occupies a prominent position in this debate. This theory posits that civilizations in the cosmos tend to conceal themselves, as revealing their location could invite annihilation. If 3I Atlas is a probe from such a civilization, its behavioral patterns, prolonged silent flight with only one signal transmitted from a great distance, appear consistent with this theory. Yet more optimistic interpretations exist. Perhaps it is merely a scientific probe, or an ancient artifact now defunct. These differing interpretations would lead to starkly contrasting response strategies. On a practical level, a fundamental choice looms. Should we actively transmit messages? Conventional wisdom in SETI cautions against hastily responding to unknown signals, but does this principle still apply to a physical entity? Proponents of communication argue this could be a once-in-a-lifetime opportunity. Opponents warn we might thereby expose the existence of Earth's civilization. A middle ground suggests first conducting deeper observations to understand the object's behavioral patterns before deciding on next steps. From the perspective of civilizational evolution, this event could become a turning point in human history. In 1492, Columbus discovered the New World, bringing two previously isolated worlds into contact, an encounter that proved transformative for both. Today, humanity may stand at a similar crossroads, albeit with potentially reversed roles. History shows that encounters between civilizations at different technological levels rarely result in equality. This asymmetry makes first contact both rich with opportunity and fraught with risk. Space law experts note that even if the 3I Atlas is confirmed as a technological artifact, existing international law lacks the framework to govern human interactions with it. The Outer Space Treaty prohibits national appropriation of celestial bodies, but contains no provisions regarding the legal status of extraterrestrial technological objects. Should it release subprobes, what would be their legal standing? If it carries messages, who would have the authority to respond on behalf of humanity? These seemingly abstract questions may become urgently pressing in the near future. Leading figures in the scientific community are now calling for the establishment of an international response mechanism. They propose forming an interdisciplinary expert committee under the United Nations framework, comprising astrophysicists, planetary scientists, diplomats, ethicists, and legal experts. The committee's mission would not be to reach immediate conclusions, but to develop contingency plans for various scenarios. Supporters argue that even if 3I Atlas ultimately proves to be a natural phenomenon, establishing such a mechanism remains essential for the future. On a personal level, this event prompted countless individuals to genuinely contemplate humanity's place in the cosmos for the first time. Across social media, ordinary citizens shared their rediscovered fascination with the night sky. Amateur astronomers organized themselves to conduct spontaneous observations. In philosophical discussion groups, conversations about the meaning of life gained new depth. This collective shift in consciousness may well be the most immediate gift 3I Atlas has bestowed upon humanity. The technological landscape is also quietly evolving. Private space companies are exploring how to modify existing spacecraft to intercept or accompany interstellar objects. Though these plans remain conceptual, they reflect the commercial sector's keen awareness of new era opportunities. Simultaneously, planetary defense systems have gained fresh urgency. If we can track and deflect asteroids threatening Earth, should we develop capabilities to counter potential extraterrestrial threats? Within this grand debate, the younger generation offers a distinct perspective. For them, the existence of extraterrestrial life is never science fiction, but a natural extension of scientific exploration. University enrollment in astronomy and astrobiology courses has hit record highs. Students organize seminars discussing how to prepare for potential contact. This generational shift suggests that regardless of the truth about 3I Atlas, humanity's understanding of its place in the cosmos has been irreversibly altered. As October 29th approaches, the day Tri-Eye Atlas will vanish behind the sun. Speculation reaches a fever pitch. Scientists stand ready to monitor any orbital shifts. Government agencies maintain heightened vigilance. The general public oscillates between anticipation and unease. This moment crystallizes humanity's entire spectrum of emotions toward the unknown. Fear and hope, skepticism and curiosity, isolation and the yearning for connection. Perhaps the most significant revelation of the three Atlas has already emerged. Human civilization is emerging from the end of its childhood. We can no longer assume the cosmos is empty, nor treat extraterrestrial life as a distant hypothesis. Whatever this particular object may be, the universe is likely teeming with life and intelligence in myriad forms. Learning to coexist with this possibility and preparing for it may be humanity's most crucial challenge in the 21st century. At this historic moment, we are both spectators and actors. Every pair of eyes behind a telescope, every voice in the discussion, is participating in shaping a new chapter of humanity's relationship with the cosmos. As the Three-Eye Atlas continues its journey, it carries away humanity's naive sense of isolation, leaving behind a civilization that must grow, one that begins to seriously contemplate its place within the cosmic family. As the silhouette of Three Atlas finally vanishes into the sun's radiance, we stand at a unique historical juncture. This is not an ending, but a new beginning. Nearly half a century ago, that single "wow" scribbled on the edge of a printed page was like a seed. Today, it has grown into a forest, transforming how we gaze upon the heavens. The most precious gift of scientific exploration is often not the final answer, but the journey to find it. During the pursuit of Three-Eye Atlas, humanity displayed its finest qualities. A global network of telescopes operating in concert, a Mars orbiter adjusting its orientation, scientists sharing data across borders, and countless eyes focused on a single target. This unity forged by the pure pursuit of knowledge is itself worthy of remembrance. Even if it ultimately proves to be just an exceptionally unique comet, this process has already driven innovations in observational technology, deepened our understanding of interstellar matter, and refined methods for studying exoplanetary systems. A deeper transformation occurred at the cognitive level. The emergence of Three-Eye Atlas forced us to elevate extraterrestrial life from the realm of science fiction to the hallowed halls of serious science. It is no longer a philosophical debate about whether it exists, but a technical challenge of how to identify it. This shift is fundamental, much like Copernicus removing Earth from the center of the universe, or Darwin placing humanity back into the natural sequence. Three-Eye Atlas has forever stripped us of the privilege of cosmic solitude, yet simultaneously granted us the possibility of becoming citizens of the cosmos. On a personal level, this event awakened a long-dormant cosmic consciousness. On social media, people shared observation experiences. At family dinners, generations debated the meaning of life. In schools, children sketched imagined starships. This collective act of looking up feels especially precious in an era fixated on earthly conflicts. We rediscovered ourselves as part of the cosmos, not merely citizens of a nation or products of a culture. Throughout scientific history, many groundbreaking discoveries first emerged as anomalies. The discovery of Uranus began with a spot of light that shouldn't have been there, while the detection of the cosmic microwave background started with noise that refused to be eliminated. The Three-Eye Atlas teaches us that anomalies are not failures of science, but opportunities for scientific progress. It reminds us to maintain essential humility. Before the infinite cosmos, we remain beginners. Simultaneously, it encourages us to preserve courageous curiosity, for it is this very curiosity that drives humanity to continually open new doors of understanding. From a broader perspective, Three-Eye Atlas may signal the dawn of a new era. With next-generation instruments like the James Webb Space Telescope now operational and the Vera Rubin Observatory poised to launch its stellar census, we likely stand on the threshold of discovering more interstellar visitors. The true legacy of 3i Atlas may be preparing us for this new era. Technologically, we've developed more sensitive detection methods. Institutionally, we're exploring international coordination mechanisms. Intellectually, we've learned to embrace the unknown with greater openness. At this very moment, on the far side of the sun, the 3 Atlas is enduring its high-temperature ordeal. When we see it again, new puzzles may emerge, and old questions may find answers. But regardless, some changes have already taken place. Astronomers now factor the possibility of non-natural origins into mission designs. Students ask bolder questions in classrooms, and each of us, gazing at the night sky, feels a new sense of anticipation. The universe remains unchanged. What has changed is the lens through which we view it. That starry sky still holds its silence, yet we know within that silence may lie stories waiting to be heard. The Atlas 3i's journey reminds us. Exploration does not end with one mystery solved, but deepens with each new discovery. In this infinitely vast cosmos, humanity's quest for knowledge has only just begun. When future historians look back on this era, they may not recall specific observational data or academic debates, but they will remember. In the 2020s, humanity made its first earnest preparations to welcome a potential messenger from another planet. This very act of preparation marks civilization's journey toward maturity. We no longer passively inhabit the cosmos. We have begun to actively engage in dialogue with it. Whether or not 3i Atlas ultimately responds, this conversation is destined to transform everything.